So I am with Educator Professional Development Collaborative, which is actually, and please don't be upset when you hear this, but actually technically I'm actually a cooperative agreement between NASA and Texas State University. Most of you don't even realize why that's an issue, so that's a good thing, okay. But I represent NASA and I train teachers to use NASA education materials. But what we're going to talk about today is just what's going on with NASA, some of the things that we're doing, some of the things that we're going to be doing. I do have information about opportunities for you at NASA, both short-term internships and what we call the Pathways program. Pathways is a longer term. It used to be called co-op, but it's basically the idea is you come work for us for a little while, you come back to school for a little while, you come work for us for a little while, you come back to school for a while. When you graduate school, we have a job for you. We're not allowed to put out the Pathways offer unless there's already a job there waiting for you to fill it. And if you've been accepted as a Pathways, it's basically your job to lose. So as long as you behave yourself and do what you're supposed to do, you're there. And you can come work for us and work with us. And I'm going to talk to you about some of the things that you can do if you come work for us and with us. So starting off just with our current vision, which is that we reach for new heights and reveal the unknown for the benefit of humankind. So why am I telling you this? Because we have multi-year missions. We're really focused in on multi-year missions right now. And those multi-year missions require people to actually be with us the entire time. But right now, a large portion of our staff are either at or very close to retirement age. If we've got a mission that starts and all of the major mission scientists and engineers are like 50, high 50s, low 60s in age, and it's a 20-year mission, we have an issue. We need some younger people to come and be those long-term people, and that's why I get to come and talk to you all. We're also developing new space vehicles, new missions, and we need new brains. We've pretty much tapped the ones we've got. Now we need some new ideas, so that's why I get to come talk to you all. And I do want to point out, because my bosses insist that I point this out, NASA has been sitting at the top of the best places to work in the federal government rankings for like the last 14 years, something like that. It's a ridiculously long time that we're just one of the best places to work in the federal government. Now, it doesn't mean the best place overall, but definitely in the federal government, we win. So come work for us, come work with us. And if you have questions, I'll give you the information to contact me and I can get you in touch with the right people. So what does NASA do? First, let me ask, I told you this was going to be some interaction. What does NASA stand for? National Aeronautics and Space Administration. So I have people who can read because it's on one of the packets that I just... So National Aeronautics and Space Administration. So we don't just do space, we also do aeronautics. Our main areas of focus, the International Space Station, the journey to Mars. Yes, we are planning to go to Mars in the not too distant future. Earth. We like to study Earth because, hey, we live here. Technology. A lot of people don't realize the amount of technology that we deal with and that we spin out. Aeronautics, of course, that's the first A in NASA. And then, of course, the solar system and beyond, the space part. So I'm going to go through each of these and talk just a little bit about what's going on. The International Space Station, our kind of theme motto is off the Earth, for the Earth. So what's going on right now? Well, yesterday, we launched a rocket to the space station, the orbital ATK Cygnus cargo vehicle, carrying new research projects, some new supplies, things like that to the station. One of the special things about that is the fact that it is the orbital ATK Cygnus. Why is that special? It's a moderately new rocket, but it's No, well, it will orbit along with the station. The big thing is that it's orbital ATKs and not NASA's. It's a commercial rocket that is resupplying the International Space Station. This is part of a venture that was started under the previous administration to expand the innovation and kind of the range of going into space beyond NASA just doing it. Because we do research at NASA. That's what we're for. We're the government agency that does the research to figure out how to do these things. But once we know how to do it, we stop doing it. And we let commercial take over doing it. Because if you keep doing it after you already proved you can do it, it's called tourism. And we're not allowed to do that. We're a government research agency. So we don't do the tourism part. Once we know how to do it, we give it to somebody else. Tomorrow, a Soyuz is going to be launching with 2 new Expedition 51 crew members. Bonus points, anybody know their names, either of their names? Either part of either of their names. Yeah, nobody ever knows it. We've gotten so commonplace now that nobody knows who's going up and down. It'll actually be Jack Fisher and Fyodor Yurichikin. And I probably mispronounced his last name, and I'll apologize to him later. But they'll be going up tomorrow on a Soyuz spacecraft. We've been using Soyuz spacecraft to send crew up and down from the International Space Station for quite a while now. People used to think and be all upset it's because we shut down the shuttle program, we have to do this. That's actually not true. The international treaty that created the space station said once it's built, we'll use Soyuz spacecraft to go up and down. Back before they started building it, we knew that was going to happen. That was part of the treaty. Some of the research we're doing up there right now, we're about to start actually we've just started VEG 03. Okay. I'm seeing some quizzical faces. For the biology majors, we're growing food in space now. We're growing plants specifically for eating. VEG 01, they grew lettuce. VEG 02 was a root vegetable, and I can't remember which one off the top of my head right at the moment. VEG 03, we have just planted, or just started, actually, it's not really planted, but we've just started sprouting Tokyo Bekana Chinese cabbage. But these are the first times, the veg experiments are the first times we get to break that classic rule, don't eat your experiments, because we're specifically doing this so we can see if we can eat these experiments. Yes? Why is NASA trying to grow Chinese cabbage instead of literally any other vegetable? Because it turns out that Bekana Chinese cabbage is quite hardy and grows well hydroponically. And dirt and microgravity, not happy together. So we've got to always grow either hydroponically or aeroponically. And it happens to be a variety of cabbage that grows pretty well without dirt. But a reasonable question. We're also doing some experiments right now with lighting effects. They're working right now on looking at how LED lights affect the overall crew mood and health using LEDs instead of using what we started the International Space Station with, which was fluorescent lights. We want to do that switchover mainly because fluorescent lights are kind of fragile, and launching things into space and fragile, again, not the best combination. So we're looking at LEDs. They burn cooler, they burn with less energy, and you can beat them with a hammer and they still work. So we're working on that right now. Spheres, UDP, is an interesting situation. Spheres are actually self-propelled microsatellites. They were originally designed to actually act as a camera system for the astronauts when they're doing spacewalks, so they didn't have to have one hand holding a camera and the other hand trying to do things. So these are little, they look like soccer balls that float around, and they've got gas jets, and they move themselves around inside the space station and outside the space station And they can set them to just kind of hover right over their shoulder with a camera, watching what they're doing, so they get both hands to work with. But the UDP is a universal docking performance test where we're looking at autonomous docking systems. And so they're actually setting them up with a docking ring and then telling them, okay, dock, and see how well they do it and manage to actually figure out how to do it, how to connect up to the docking system so that we can make these advancements in autonomous docking and we don't have to use. Right now, when an autonomous vehicle comes up, most of the time what actually happens is that right at the last little bit of docking, one of the astronauts takes over and pilots it in using cameras and a remote control system. We'd like to do it without the astronaut being involved, so it just docks and they go, oh, yeah, it's here. We should go empty it now. And then some additional human research that we're doing. We're doing biochemical profiles in space. We're looking at some functional immune system experiments. We're doing a vascular echo experiment right now where they're actually doing ultrasound ultrasound on the vascular system to see how the heart changes during space flight. Because microgravity really messes with the human body. Because our body's developed to work in gravity, and when you take the effect of gravity away, the body freaks out. And so we're trying to figure out how exactly it's freaking out so that we can figure out how to fix it for long-term space trips so that we can continue on with some other things. So here I have a shot of, that's Fyodor and that's Jack. And those are nobody. Those are their suits, actually, that they wore, or will be wearing, I'm sorry, tomorrow when they launch. And that's where we're talking about going, the International Space Station. Anybody know how big that is? Oh, okay, well, that's fair. It is roughly the size of a football field. It has roughly the living space or pressurized space of a house. But it uses the energy of 3 houses, which is why we have all the solar panels. Because you have to do everything. For example, if you want it a little bit cooler, it is not recommended to open the window. So we have to have fans to blow things around all the time. It also turns out, and this is one of those you're going to need to talk to your professors about a little bit, if we don't run our fans continuously, you can kill an astronaut by telling them to stay still. Because air works on density flows. And so when we stay, like you guys all sitting there right now, as you exhale, the air is warmer, it gets pushed upward by cooler air that drops in, and the air gets refreshed right in front of your face because gravity works. In a microgravity environment, you exhale and then inhale the exact same air, unless somebody blows it to the side and puts fresh air in front of you. So you can actually, just by staying, if you all were just in place in the International Space Station and we turned off the fans, right now, none of you would be awake because you would have taken all the oxygen out of the air that was in front of you and you'd be starved for oxygen right now. So we've got to constantly be running things. Moving on, one of the reasons we're doing all this on the space station is we want to eventually go on to Mars. Right now, we are what we call Earth reliant, now through about the 2020s. Earth reliant simply means we have to keep coming back here or get stuff from here to stay alive. We are continuing with ISS operations, the International Space Station, until at least 2024. We are encouraging commercial development for what we call LEO. Anybody know what LEO is? Not a really cool name for a cat. LEO is low Earth orbit. So where the space station is, basically. We're looking at helping commercial companies develop their capability of going into low Earth orbit. Because if they can take that over, then we can concentrate on learning how to do other things. We already know how to do low Earth orbit. We are also working on the development of deep space technologies. Those are the things necessary to get us out to Mars. And we're working on the Space Launch System. Anybody know what the Space Launch System is? You're breaking my heart a little bit. Space Launch System is our new cargo, our new heavy lift vehicle that NASA is building. It looks vaguely, or it will look vaguely like that, although not exploded out like that, we hope, because that would be bad. But this is the new heavy lift vehicle. When it is built, it will be the largest vehicle to ever have gone into space. In the small configuration, which is what you're looking at here, the Block 1B, this vehicle is 326 feet tall and is capable of carrying 70 metric tons of cargo into space. Yes, sir?
How does that compare to the Saturn V?
The Saturn V was about 30 feet shorter and capable of carrying right around 30 metric tons. So quite a bit less lift capability. In the large configuration, which will be Block 2, that's the real heavy lifter. That will be 365 feet tall and capable of carrying 130 metric tons, roughly the equivalent mass of 21 adult elephants. Not that we're planning to take 21 elephants into space, that would be weird, but roughly that size. But this right here, the crew module, that little bitty piece is where the people go. Everything from here down, all of this, gets it all into low Earth orbit, and then these take it beyond low Earth orbit. But this vehicle will be able to send things out to Mars and beyond. And that right now is something we don't have the capability of doing. Here and then here. Actually, the tonnage that I said for lifting is cargo tonnage, not the rocket itself. It'll lift itself plus that cargo. But from here down, yeah, it's the engines actually are in the white spot here, and all the rest of that is fuel. And over here, it's actually, these solid rocket boosters are actually fuel all the way up. They're just a nozzle at the bottom, basically, and then solid fuel all the way through. It's sort of like a giant bottle rocket, really, honestly.
I get that the point is to go to Mars, like, awesome, but is there a practical vision for this, like a end goal that you guys are trying to get to?
There is. There's two actual main end goals to it. One is there's more we want to learn about Mars, and we want to be able to actually determine whether we can put people long-term on another body, because we're running out of space on this one, in case you hadn't noticed. But the more important one actually is that in doing this research, we are developing new technologies constantly, and those new technologies end up with applications here on Earth. So a large portion, and this happened with starting all the way back with the Apollo program, a large portion of the Apollo program, the worth of it was not in actually getting to the moon and bringing back the moon rocks that we brought back. That's cool, but it doesn't help a whole lot of people. But the technologies developed in the process are the big thing. Already the technologies that we're developing to make SLS work, we've made major advancements in water filtration systems, in fuel, in developing high-speed turbo pumps. It actually turns out one of the turbo pumps for the engines down here, a miniaturized version of it is right now in human trial testing in Europe as a new heart. Not quite at the same rate of pumping for this, but because that would just really bother people, but the same technology. So that's a large portion of the end game. We're not just doing it to see if we can do it, although it's really cool if we can do it. Don't get me wrong. So our next stage is the proving ground from 2018 to 2030. And by the way, SLS first launch should be fall of 2018. So next year in the fall, be looking for a big honking rocket to leave Earth and probably go to the moon. We're looking at regular human operations in what we call cislunar space, which is basically around the moon. We want to verify deep space habitation. One of the things we're most likely going to be doing is setting up a habitat on the other side of the moon. and we're going to stick people out there for extended periods of time, because honestly, going to Mars in that little bitty capsule I showed you where the people go, not going to happen, because the trip to Mars is about 9 months. And that capsule, you can fit almost 2 of in this room. And they're planning to put 6 people in it. Can you imagine picking 5 of your closest friends and spending 9 months in a quarter of this room?
Yes, that sounds like Camel Fall.
Okay. You do have a point there. Maybe we should be looking at college students as those astronauts. I hadn't thought of that. I like that. So this should be a commonplace thing in that starting 2018 time frame. This is the SLS, a graphic of what we think an SLS launch will look like. Yes, sir?
How much of that one is reusable? Like, are the solid rocket boosters right now, are they reusable?
The solid rocket boosters are possibly refillable, reusable. Right now, the plan is actually not to, but they are capable of being refilled if we recover them. The rest of the rocket is not reusable. Right. Right. So we've gone back to, yes?
How much funding goes towards that?
How much funding goes towards that? Exact numbers of funding, I don't really know, but I can tell you that the total NASA budget is less than 0.1% of the US budget. So for every dollar of taxes that are paid take a penny and then cut it into 10 pieces, and all of the science done by the US government is done with that 1/10 of a penny. And we're one of the agencies that does science for the government. So we're less than 1/10 of a penny of every dollar of taxes. The overall long-term development, it's in the several hundred million, possibly up in the billions, but I don't know the exact number. Yes?
Don't you also have private funding?
We do not. We encourage private industry and we spin out to them, but no, we do not get funding from private. We actually go the other way. We give funding to private to help build them. So starting in the 2030s and on out, we hope to hit Earth independence, meaning we don't have to keep coming back or getting supplies from Earth. We can do things on site. So we're talking about science missions to Mars where they stay. We're talking about entry, descent, and landing, and in situ resource utilization. So we're actually taking what's already there and making it work for us so that we don't have to keep resupplying from Earth. Towards that end, in the late 2020s, we're planning a robotics round trip with a sample return. Because right now, we've gotten to Mars, we've landed things on Mars, we've driven things around on Mars, we've collected samples on Mars, but we've analyzed those samples on Mars. We have not been able to send them back to Earth to analyze with all of the possible instruments. You have to guess what instruments you might need and send them up right now. We'd like to go grab some stuff and bring it back, and then we can go, hey, what if we tried this? And we could actually try it. Yes?
How do you go about selecting the people for these trips?
How do we go about selecting the people? For this trip, there won't be any people, but for the astronaut where we do science missions to Mars, they'll be selected from the astronaut corps, and that corps will consist of people closer to your age than my age at that point. The last thing we want is that first rocket to land on Mars and the astronaut to climb down the ladder and reach back for his walker. It's just not going to work. So it's much closer to you guys right now than it is to me for that. But it's a matter of becoming an astronaut and then being selected for the mission. Once you've gone through your probationary time as an astronaut, you go through about 2 years of training before you're allowed to be selected for a mission, and then after that, you get selected for a mission and start training for it. But they actually haven't even set up one of the things will be a psych profile, and they haven't even written the psych profile yet because it's far enough down the road that we're not ready for that part yet. And we're talking humans orbiting Mars early 2030s, which means we better get on it in selecting those astronauts and starting to train them. But We're talking about the early 2030s for humans orbiting Mars. We're talking about humans walking on Mars around 2036. Boots on Mars is our goal, around 2036. We've already started placing things on Mars. The Mars Science Laboratory rover has science instruments on the back of it, specifically put there so that astronauts could be walking next to the rover and pick stuff up and start analyzing it from the back of the rover. It's actually was designed with a controller. It's autonomous right now, or semi-autonomous right now, but it was designed with a controller that the astronauts will be able to walk along next to it using the controller, which looks amazingly like a PS3 controller, most likely because it started its life as a PS3 controller before they hijacked it and started building it into control for this. But this is our architecture of things we're planning to do. We're right here right now. We're almost here. And then we've got to continue on to this to get out a little further. Yes?
You said you already have things on Mars.
Yes.
And are y'all getting feedback from stuff like that? Or y'all just, I guess, do y'all monitor just obviously to see if there's a lot of
We are constantly monitoring what they're doing and what information they're getting, and yes, we're constantly checking for life, because one of the other fun things that we have to do right now in this time frame that we're in is actually prove that either there isn't life on Mars or that we can be clean enough not to kill what's there, because we can't go if we can't prove that. It's against international treaty. Yes, most drastically. We actually do, for those of you that are Trek fans out there, the Prime Directive, there is a version of that that's part of international treaty that basically says you can't go somewhere that you might kill off things like we've done in the past when we've colonized places. So we have to be careful. And if we find that there is viable life above a certain level of single-celled organisms that we can't protect, then we have to change the plan completely. So talking about Earth, your planet is changing. We're on it. Get the joke. Okay, moving on. So they thought it was a lot more clever when they came up with it. Yes?
Before we leave Mars, real quick,
Sure.
what is the idea for the craft that will make that 9-month journey? Because we can't go in little capsules. So what's the thought on that process?
We're looking at building. That's actually why that habitat goes just beyond the moon, and I kind of stopped and moved off of that. But the idea is put people there, and they will build a larger vehicle that will then be able to go out to Mars from just beyond the moon. Exactly what that's going to look like, we're not positive.
About every 4 to 8 years, our government administration changes.
You've noticed that too.
More pro-science, some are probably more anti. How much of that would probably affect your timetable or your plans?
We're waiting to see right now on the most recent change. But as it stands right now, Mars is still on the books. And that's the best I can say at the moment. But so far we've had pretty strong public support and congressional support. So it hasn't seemed to have a huge amount of shift. Yes?
How long is it from
Earth to the moon, how long in terms of distance or time travel? Time to travel, about a day and a half to 3 days, depending on how fast, how many loops around the Earth you plan to do first. So yeah, it's a slight difference between that and going to Mars, where it's about 9 months.
And what's hypothetically, could you grow anaerobic bacteria on Mars?
Hypothetically, yes. There's quite a bit of carbon dioxide. It's a very thin atmosphere, but there's enough to do all kinds of fun things with anaerobic bacteria and things like that. Yes? Mars is the closest one that won't kill us immediately. Well, Venus is not too far away either, but Venus has this really thick blanket of greenhouse gases that keeps the average temperature at roughly the same temperature that you cook turkeys at. The air pressure is about 3 times what we find here on Earth at sea level, and when it precipitates, it's pure acid. And those are generally considered bad for people. So we can't go to Venus. Mercury, on the side facing the sun, the temperature is right around 500 Fahrenheit. On the side facing away from the sun, it's right around negative 250. That's not going to work.
Soviet probes that landed on Venus back in the 70s were crushed within an hour.
Yes, yeah. Everything we've ever landed on Venus has been destroyed within 2 hours. And nobody volunteers for that mission for some reason. But Mars, we think we can last on Mars for a while. We've had rovers and things last on there for a long time. Moving out from Mars, you're ending up with gas giants, so you'd have to go with their moons. And we're really interested in some of the moons right now, and I'm going to talk about those in a little bit, hopefully, if I talk faster. Any other questions before I move on to Earth? Yes?
Do you plan on making Mars a more, agricultural endeavor?
We're going to have to grow food there if we stay there for a while.
So like the Martian?
Similar to the Martian, but hopefully better. More than potatoes. And we're actually, and I'm going to talk about, we're actually looking at how do we make the Martian soil work for Earth plants right now. That's some of the research that's going on.
And will the difference in gravity affect it? Is that why you're...
The difference in gravity is actually not that big. It's about half Earth gravity. And as far as plants are going, they're like, yeah, whatever. They're really good with it. We can go down as low as a 6 Earth gravity, and the plants are like, okay, cool. But it's microgravity where the plants start freaking out a little bit. But yeah, that part is fine. We are not looking at terraforming Mars. Okay. Yeah, there's a whole lot of issues with that. There have been some ideas floated out there, but right now that's not in our plan. So the black marble, Suomi NPP is a satellite. It's the Suomi National Polar Orbiting Partnership. It's an international partnership satellite that's been logging information about the Earth for quite a while. You've heard of Earth called the blue marble. Why is it called the blue marble? When is it blue? It's blue when you look at it in the daytime, when the light can hit the oceans and bounce off and you get the blue reflection. But at nighttime, it's black. The black marble that we're talking about here is they are figuring out ways to process the data from Suomi NPP faster, such that we should, in the very, 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 very near future, like maybe this year, be able to look at real time, this is what the Earth looks like at night. The last time we did a global, this is what the Earth looks like at night, it was 2007. They're talking about being able to update it like, you could look at it today and then look at it tomorrow and possibly see differences. They're working on image processing to take out clouds and things like that. You've got to do it as a composite image because the Earth is not dark all over at one time. That would be bad. But we'll put together the images, and within a 24-hour period, we should be able to actually reprint a black marble and see what's going on. It's interesting when you look at the lights from Earth, the things that you can see when you just look at the lights that are on at night. There's some really, really interesting stuff you can figure out. We are partnering more closely with the U.S. Geological Survey right now. In fact, they are now they're in the process of moving right now to the Ames Flight Research Center in California. They're moving about 4.5 miles from their offices to be actually on Ames to work with us so that we can combine and study our planet from orbit to core, learn everything we can possibly learn. That's actually a very big deal that we're getting that kind of partnership finally happening. We've been working on that for about 18 years, and they're finally moving in together. Just for a trial period, we'll see how it goes. But we're also looking at some interesting new data on global precipitation. We've had some researchers just figure out how to take pictures of snow and figure out how much water is in that snow. Why do we care about that? Well, it's easier to measure that way because it stays still, which is helpful. But the other big one is snow is fresh water. You don't get snow out of salt water. So if you know where snow is and how much water is there, you know how much fresh water you have available in that snowpack for people need fresh water. Turns out it's one of those essentials. So we like to know that kind of stuff, and we haven't been able to figure out, all we've been able to do so far is say, well, there's snow there, and we know there must be water, but we have no idea how much. We're now data processing such that we can actually figure out exactly how much water, which is going to be exciting, I think. And I do want to just mention EO1. EO1 is one of my favorite Earth-observing satellites because EO1 was launched in 2000 on a one-year mission that was a testbed mission of 14 different technologies for studying the Earth. EO1 finally got powered off March 30th of this year. For the last 17 years, this one-year mission has been giving us data about the Earth. I like to emphasize that because one of the things we want to emphasize to people who might come work for us is we're building for longevity. This is a one-year mission that operated for 17. That's why we need younger people to come in and help us out. Because the guys that were 60 and on this one-year mission were like, cool, we'll be there till it's over. Didn't work so well. That's EO1. Well, no, that's a drawing of what EO1 would look like, but that would be the black marble. The North America, or the, North America and South America part. Where you can see kind of cool things like, anybody know what this stretch is? Yeah, we call it sometimes the Northeast Corridor, or the megalopolis. It's from Washington, D.C. to New York City. You get Washington, Baltimore, Philadelphia, New York, and it's almost a continuous stream of bright, which means they don't get to see the stars we get to see here because there's too much light. By the way, we're right about there in that dark spot right now, sorry. Troy does not put out nearly as much light as you would think. So technology. Remember, this is one of the big things we do is develop technology. So we have something called the NASA Innovative Advanced Concepts, which is grants and awards. Okay, we just announced about a month ago Phase 1 and Phase 2 concept awards. Phase 1 concept awards, these are the, hey, I've got an idea, I need some money to figure out whether it even makes sense as an idea. So we have grants of up to $125,000 for 9 months of figure out if this is really a real idea or you just really should calm yourself down. And then we have Phase 2 refinement awards. We've got 7 of those we just announced of up to $500,000 for 2 years of, okay, it's a real idea, now make it a viable idea. These grants go to NASA scientists and engineers, collegiate research, and international partnership research. But I can tell you, let's see, Georgia Tech got one for an evacuated airship for Mars missions. Space Studies Institute in Mojave, California got one for Mach effects and space propulsion. There's currently one they're looking at for taking Mars soil and making it plant viable. That one's in one of the Phase 2 research. So we're doing a fair amount with that. We also have something called the Technology Transfer Office, which develops what we call spin-offs. NASA is a government agency, which means we cannot hold a patent on what we develop. So we're doing all this innovation, we're developing all these new things, these new processes. We cannot own them. So the way that it works is the Technology Transfer Office works with industry. And basically every time something new is developed, It goes to the tech transfer office and they say, hey, we have this new thing. Can anybody make money from this? And a company says, yeah, we'd like to try. And they say, here, go do.
And you get no money from that?
We get no money from that. That's part of the job of the US government. We get nothing, no kickbacks from that. We get a little prestige when they say, hey, we did this from NASA stuff, but otherwise, no. That's how it works. But, you know, all of those, anytime you see a commercial where they say, you know, from NASA Space Foam. Well, no, it's not really from NASA Space Foam. It's from a technique for developing foam that NASA developed and then put into the tech transfer office. And so they got the idea or the process from NASA, and so they call it NASA Space Foam, or what was it? They were running one for a while where they were talking about from NASA zero gravity seats, and everybody, I got constant questions. Wait, we have seats where there's zero? No, we don't have seats for zero gravity. You don't need seats in microgravity. There's no reason to sit down. You don't get tired from standing if you float. But the foam that was in the seats was developed with NASA, so that's where it came from. This shot I just like. We just recently came up with a new technique for developing thermal shields for re-entry. And this is actually the animation of the way that the thermal shield works. It's a non-ablative shield that can be produced very, very quickly. And so we're looking at it for re-entry of commercial vehicles from space. Aeronautics, because I'm like way over my time, aren't I? Oh, well. I'll keep talking until they tell me I can't talk. So Aeronautics Advanced Air Vehicles Program, we're basically developing new vehicles, new aeronautics vehicles. Then the Airspace Operations and Safety Program, this is looking at the next generation of air traffic control, of systems. We're actually helping develop systems right now that instead of having to declare a no-fly zone and deploy aircraft to go turn people around when they're flying in the wrong place, the next-gen system, one of the things that they're looking at is actually a system that as the airplane starts coming into the no-fly zone, they get an automated warning, hey, you're coming into a no-fly zone, you need to turn. They move a little closer, they get another warning that says, you're going to turn now or we're going to turn you. They fly a little closer and we take over the aircraft and turn it and land it where they can be met by people who want to know why. Without any control, anything that we have to do, we don't have to scramble jet fighters or anything else. We just take care of it. That kind of technologies we're working on to help out. The Integrated Aviation Systems Program is transitioning new technologies into actual vehicles. And then the Transformative Aeronautics Concepts Program is coming up with the new technologies to then be passed off to them to be put into new vehicles. And that's where we get these wind tunnels with things like this. That's actually a fused wing body design that they're testing in one of the wind tunnels. And then the solar system, because we are part of this solar system. So by the numbers really quick, how many planets do we have? 8 planets. How many moons do we have? Okay, I gotta wrap it up. So I'm gonna go faster. We have 178 known moons in the solar system. We have 5 dwarf planets known in the solar system. Pluto's one of those. We have 732,323 asteroids and 3,465 comets. By the way, one of those asteroids is right now passing closer to Earth than most things ever do. It's only 1.1 million miles away, or about 4 times the distance to the moon, which astronomically speaking is like, we got to get out of the way, but we can't do that. We have 1 star. We call it Sol, or the sun, most people call it, but its real name is Sol. So what are we doing? Right now, connect conditions for life. We have found recently that 2 of the icy moons of the gas giants actually have the necessary water and other minerals for possible life, Enceladus and Europa. Enceladus around Saturn, Europa around Jupiter. The Cassini spacecraft that checked out Enceladus is actually coming to the end of its mission. It's been in operation for 20 years. It starts a final flyby of the moon Titan in 3 days. It'll start a deep dive where we're actually dropping between the rings and the planet. First time we've ever done something like that. It starts those deep dives on April 26th, and on September 15th of this year, it will plunge into Saturn and be lost to us. But it'll check things out until it gets squished and stops talking to us. That would be an artist rendition of Cassini going by Enceladus. And I just want to end with where we are. These are the NASA centers where you could possibly come and work for us or work with us. So now, does that mean that you can't do anything for NASA up here? Absolutely not. I did not include all of the NASA researchers at various universities that are working with us because you wouldn't see the map. Any questions? Last questions. Yes?
You said the thing that's near Enceladus, it's talking to us the whole time and it's going to crash in Saturn. But if it's so far away, how are the messages getting to us?
We actually send them through microwave transmissions. So it's got a transmitter on the back of the spacecraft and it just points at Earth and sends, and then we collect it with large satellite dishes.
Is that the same microwave that's in the box in my dorm room?
It is, but not concentrated the same way. By the time it gets from Saturn to us, you have to have a very, very sensitive detector to even know it happened. Yes, sir? Or ma'am. How has the hiring freeze affected us? It has affected hiring of civil servants, although the freeze just got lifted last week, I believe. But as far as pathways, it actually turns out that it did not affect pathways. I think I'm done now. My pleasure.